welcome to my humble video. My name is Professor Chuck Bland at California Polytechnic State University in San Luis Obispo, California. Let me give a quick plug to the music before we get into the video here. That was a group by the name of Funky Times. They're out of Germany, a nice, tight funk band that you want to look into. I'll put their website in the show notes so you can look them up if you want to. Check them out, buy their music. The intended audience for this video, presuming you're in it, are students new to the Vector Network Analyzer. We'll call it the VNA throughout this video here, and its use. And the objective is to introduce you to VNA setup and calibration. Now, this can be a really deep subject. We're not going to go really deep on it. We don't have to show you the initial hows, what you need to do, and whys we need to do it. Now, correct calibration and verifying that it's been done properly is usually the single most frequent source of problems that I see in the lab when we're dealing with the VNAs. Something's not working. Sure enough, the calibration was not correct. So this is worth taking the time to get clear instruction before you get onto this work. Please don't fast forward through this video. You will miss important details. I know it's going to be a little, 30 minutes-ish, but it's going to be worth your time, and it will make your use of the VNA all the more satisfying and stress-free. Let me also encourage you, if you haven't done so already, to go to ee.calpoly.edu/manuals and download this document right here, bunch of paper. It's called the E5080B VNA Quick Reference Guide. It's in the technical notes section at the top of the page. The calibration procedure is covered in detail in the document. You can use that to follow along as we do things in this video. So please go get that, check it out. We got 4 areas that we're going to cover. We need to understand why we're doing this in the first place and the parts that contribute to this. We need to know what a DUT is. We need to get a handle at least on the 2 basic setups that we're going to be looking at, single port and 2 port. And we're going to talk about calibration planes and reference planes. The second major area is the calibration process itself. We're going to be doing what's called an SOLT calibration, so we'll do an overview of that and a demonstration as well. We will demonstrate that calibration procedure for you to watch on the on the VNA. And we'll also talk about calibration validation. How do you know you did it right? And how don't you know that you did it right? Because there are some assumptions out there that are no longer correct given the current state of the technology of VNAs. So we'll want to check into all that. So with that, let's dive in. Understanding the need to calibrate a VNA. So we have our VNA. We have our device under test. We want to measure the device under test with the VNA. This is the thing being measured. We have cables and connections in order to get to it. All of that helps us establish physically the calibration reference plane. This is the point at which we can take calibrated measurements, and we know that our cables and connectors between the VNA and the device under test are not contributing to our measurement. That's the whole point of calibration. Let me read for you. It's on the screen here. A definition from National Instruments for the reference plane. In a VNA measurement, the reference plane is known as the location within the system where the user calibration is performed and is therefore the plane where the measurement is typically made. This is all true. This is the definition that we're going to be working with here. Here's a photo. I kind of coiled the wires up here just to get them in the photo and so you could see the connectors as well. 2-port setup here on the front of my VNA. A pair of VNA cables that are good to 6 gigahertz. These are SMA, also known as APC 3.5. That's the newer, better name, and these are conformant to that. SMA isn't exactly the same thing, but for our discussion, it's going to be close enough. So every once in a while, if I slip and call them SMA connectors, I really do know these are SMA 3.5s. So this diagram here is showing a 2-port setup. 2 VNA ports connected and calibrated. This lets us do reflective and through measurements. Stated another way, we want to do this when we want to measure through something. Now we can do a one-port measurement where we have only one port involved. This enables reflective measurements only. How well are we interfacing to this point? Are we delivering all our power to the device under test, or is some of it being reflected or has some other problem? State this another way, we do this when we want to measure to something, not necessarily through something. So our test cables and our connections introduce errors and changes to the measurement. That's the whole point of calibration, is to eliminate that from our measurements. We can quantify and correct these in our measurements in real time. It's quite an extensive process that the machine goes through. Don't have time to get into it here, but it's fascinating. So then calibration establishes our reference plane as a location where measurements are taken. Errors up to this point are known and can be removed from the measurement. Now we need to remember this. Once our reference plane has been established, we need to do our best not to change it. We need to, if I can say, defend it. So if you change cables or add adapters, you will need to recalibrate to establish a new reference plane that includes the new components, or remember that the new components are contributing to your measurements. You just have to take that into account. Let me illustrate it with this. This is a picture of a low-pass filter with SMA connectors on it. Measuring this is not the same as measuring this. Here we've added the adapters, and these adapters affect our measurement. So if our reference plane, I know I'm taking liberties here with the connector types, but if my reference plane is out here instead of right here, then I have added whatever loss, albeit small or large, is contributed by this adapter here and here. So these two measurements are not the same. All that just a plug. You got to protect your reference plane. The calibration process, that'll demonstrate. We'll do that on the screen here. And it's also available in the quick reference guide. Told you where that is, eecalpoly.edu/manuals. Go to the Tech Notes section. The process, fundamentally stated, is we've got an open, short, and a load if we're doing a single port calibration. And we apply each one of these to the connection and tell the instrument, okay, I've connected the open. All right, I've connected the short. Okay, I've connected the load. It does some measurements, builds its tables based on what it knows, and then prompts you for the next one. If we're doing two-port, we have to apply all these loads to both ports. And in addition, we have this one through connection, which would be a barrel connector most of the time. With all these activities, then we've established our calibration planes, and we're now ready to move on and measure our device under test. You need a calibration kit to do all that. That's where these things come from. These kits contain what we call calibration standards: the open, the short, the load, the through. Usually the loads are 50 ohms. In the RF world, it's 50 ohms. There are some situations out there that are 75, but for the sake of this course, it's always 50 ohms. So this is an SO, L, and T kit. These standards are made to precise known values necessary for the calibration process. Because of that, they can be very expensive. We've got some cheap kits that we use. Yeah, I'll admit to that. But they get the job done for us for most of the demonstrating that we're going to do. Real cal standards can run upwards of $1,000, typically more like $10,000 to $20,000. They are mechanically precise. They are repeatable. They are stable. The loads themselves are precise. It sounds a little weird to say this, but there is such a thing as a precision open and a precision short. And of course, a precision load, you want it to be as close to 50.00 ohms as possible, because know that with an open we have a defined gamma, with a short we have a defined gamma, and with a 50 ohm load we have a defined gamma. So we need for these to be accurate so the instrument can take accurate readings for the calibration process. So let's look at what some of these look like. So I'm going to drag over my cal kit right here. Let's start with the shorts. Pretty small, so it's not going to be just real easy to see. This is the female version, this is the male version, and this male connector looks like the one on the cable that I showed you earlier. There's a pin in the middle. The only difference between this one and the one in the photo is this pin is actually manufactured in such a way that it's connected to the outer case so that it is a short. We have 0 ohms, 0 impedance, so we have a gamma of -1. It has known inductance and known delay because there are distances involved, right? If we go back to looking at this, there is a distance where the actual short is versus where the connection is made to this. That contributes delays and phase delays. However, all that information about these distances and delays and inductances are known in a data file that is put in the VNA so that when we select this particular cal kit, it's got a name here, Cal Poly Bench Cal Kit. When we select this particular cal kit, then all these characteristics are known to the VNA, including its inductance. So we have this inductive behavior that gives us phase lags. This helps us characterize cable losses, including its phase loss, its alpha, its beta, and its magnitude errors. We also can measure the inductive effects on the test setup. And then last but not least, we have phase magnitude errors because of that reflection coefficient being -1. All right, let's move on to the opens. Mechanically, they look pretty much the same. The main difference is in here, there is no center pin. It is basically a ground cap, but it doesn't ground the center pin, so it's an open. There is still a distance, and with that there is some phase delays. There will be some stray capacitance, which will cause phase leads. These characteristics help us define things in the cable like its loss, phase, and magnitude errors. We can also characterize the capacitive effects of the test setup because we know what's in that calibration standard, so any additional capacitance we measure we know has to be coming from our environment. And then we can look at phase and magnitude errors because we have a reflection coefficient of +1, and we will see them in a slightly different light because of that. The load looks kind of like the short, with the exception that instead of 0 ohms, we have 50 ohms. These, you've been noticing, are all color-coded. That's how you can tell the difference between them in the kit, because mechanically they look pretty much the same. Since the load has the same impedance as the transmission line used in the test setup, it gives us a gamma of 0, and it tells the analyzer what a perfect non-reflective DUT would look like, and thus reveals certain other aspects of the test setup relative to perfect conditions. So we need all three of these, and the VNA knows how to do the analysis on them in order to determine what the test setup is like and how to compensate for it. We have a through, and it is these barrel connectors, one each male and female. Since they have physical distance, there is delays to them as well, in phase and losses. These are all specified in the CalKit definition file so that the analyzer knows what to do with this and knows the difference between what the connectors are contributing and what it's seeing in the cables. Now we need to talk a little bit, I kind of alluded to this, but we need to talk more about how Cal standards are made. Most but not all of the Cal standards you're going to encounter will have a small distance between the connector and the actual load. So the short is some distance away inside this standard. Likewise, the open occurs some distance away from the connection to the cal standard. So this point here where we make our connection is actually our reference plane, and then the actual loads are out here toward the ends. Now the short, as you can see by this reference here, we've got some inductance to deal with, and with the open we have some capacitance because, well, it's two conductors separated by an insulator, right? I'm going to call these distances offset delays. In our VNAs, it's called port extension, and this distance is significant because it extends the standard some distance beyond the reference plane, and if we don't correct for it, we're going to have errors. These are known. I'm going to mention this again. When you select the cal kit in the calibration process, it pulls up all the parameters for the various loads. So when you say, okay, I've connected to short, it's got access to information to know what it should be seeing and how that is contributing to the measurement so it can compensate for it. But this information is only used in the calibration. We will revisit this when we get into the validation. Just for now, know that the offset exists and it is automatically compensated for during calibration. So the process, let's review this one more time. Generally straightforward. We connect each of these standards to our mechanical reference plane, the point where we're going to establish the reference plane. We click the button telling the VNA to test for that particular standard. There will be a button unique to each one of these four. We repeat for all standards on all required ports. If we're doing one port or two port, we still have to touch the port connections with each of these standards. And then you're done. That's it. If you're performing a two port, you just got to do it on both sides. In that process then, we're going to collect some data in the analyzer. And we're going to do this for each frequency point because part of the calibration process, we say we are calibrating across a particular range from a start to a stop frequency. And so we collect data at each of those frequency points, and I'm going to call it TL1 and TL2. These are for transmission lines 1 and 2, our test cables. So I've got this characterized data. This is calibration data that's going to be used. So when the VNA takes a measurement of everything, we're going to get the measurement of that DUT plus this calibration data collected by the analyzer. In its processing, we get our DUT data simply by removing this calibrated data from the measured data. So we subtract TL1 and TL2 from it to get our device under test information. Now, in reality, is far more complex than that. There are dozens of terms involved, quite complex. It's the subject of lots of ink spilled on white papers, and it's out there for you to research if you like. But just for our sake, know that we take a measurement, we subtract the calibration data that we've got, and that leaves us with our DUT measurement. So let's summarize. Calibration process applies conditions known to the VNA during the calibration process. We will call this the test setup. Variations from what is expected during calibration are due to the characteristics of the calibration setup. These variations are referred to as error terms and are collected at various frequencies across the specified calibration frequency range. These error terms are used to correct measurements and present accurate readings to the user. Since the test setup can vary with cables, connectors, adapters, and so on, calibration must always be done before measurements can be made. All right, so let's take a look at the whole calibration thing. Let's take a look at these cal kits in their entirety. Showed this one already. This is the one that you'll find in the benches here in our transmission line labs. These are good to actually 3 gigahertz. It says 2.5 here, but they will go to 3. And the lid here is color coded so that it will help you figure out, yes, these are the shorts because they're green, these are the opens because they're yellow, and these are the loads because they're red. These kits also contain the throughs that are needed and some attenuators. This extra stuff is here just because I'm going to use it today. We have another cal kit. Actually, we have several different cal kits here at the university for your use, depending upon what you're going to be working on. This one here is made by Antonex, and it is good to 15 gigahertz. This is a serial number on here because each kit that you buy from them is unique. They characterize their shorts, opens, and loads. This little open slot right here is where the thumb drive goes that had the data with it. I've saved that out of there so that it doesn't get lost. But we have built calibration kit files for the VNA for these kits. So when you check out kit number 828, you can select kit number 828 in the VNA, and then it has all the characteristics of this particular kit. The kit also includes throughs. This is the male through. Here is the female through for the kit. Again, these all have known delays, and that was given in the specifications. We have a 3 dB pad that's included with the kit. And it also comes with 2 wrenches. Now, this is kind of important. This is a 5 inch-pound torque wrench. And this is to be used when you are tightening connectors onto the VNA or to other items so that you do not over tighten them. It is amazing how much, I call it gorilla tight, that students will over tighten these things and then they can't get them off. So you use this, and when you get up to 5 inch-pounds of torque, then the wrench automatically bends and tells you, okay, that's enough. Now, included with the kit is a non-torque wrench, and this is used to hold something still that you're tightening against. So this is on the connector that needs to have the controlled torque. So these are all part of most of the cal kits that we have here. Our test cables that we have here are 20 inches long, and these are in our benches. They're made from RG316D. They have a max useful frequency of 6 gigahertz. By coincidence, I am at bench 6, which is why you see a 6A on this label and a 6B over here on this label. This just tells you I'm working at bench 6, and these cables belong to bench 6, so that when they're done, you need to put them back in the resource drawer for bench 6. One note of treatment of cables. Yeah, they're thin. Yeah, they're floppy and wobbly. Please don't put hard bends in them, because those bends actually cause impedance inconsistencies and pretty much render the cable useless. So treat these as you would any other precision equipment. We need to take care of them so they last. They cost us money to replace. We don't want to waste money. We need to keep that in mind. So please take care of the equipment. Let's talk a little bit about calibration verification. If we want to verify that our calibration was done correctly, there's a temptation that we'll have to simply remeasure the standards. After all, I've got a precise 50 ohms, I've got a precise open and a precise short. Shouldn't I then be able to hook these up to my cables and then see a dot for the load and a dot for the short and a dot for the open? Shouldn't that happen? Well, it's not going to happen the way you want it to. Remember, I talked about these offset delays. They're here because of how each of the standards are made. And these delays are known to the VNA during calibration only because of the cal kit. This information is irrelevant when you're actually measuring, because you want to measure this whole thing. And the VNA has no idea you've just connected a calibrated short or a calibrated open to it. It just knows you've hooked something else up to it when you're not calibrating and only measuring. The measurement isn't wrong. It's just including everything it's seeing. The bigger problem might be it's not what you're expecting, and we'll talk about why. I also mentioned that we have these stray capacitances and inductances in these, and they will show up. They are proportional to this length here, and of course the frequency, and so it will show up as inductive reactance and inductive capacitance. However, the shorter the offset, the closer that measurement will be to the dot on the screen. And it's some pretty high-priced cal standards that have the 0 offset on them. They're very rare, and you got to have a specific reason for wanting to spend the kind of money you'll have to spend on them. You can see from our diagrams here, where our reference planes are. And when we combine the two connections together, we still end up with this reference plane, but we've got some distance until we get to the open or the load. And that's where these stray inductances come from when we do the measurement. So here's an illustration. These are actual traces. This is when I connect my calibrated short. Notice at the low part of my sweep, I am at 0 ohms, and as frequency goes up, here's 1 gig, here's 2 gig, here's 3 gig, that I get more and more reactance, and that's why I see this arc. I'm supposed to see this when I am measuring one of my calibration standards. Likewise, on the open, I'm starting here at infinity, and as frequency goes up, I am seeing the stray reactances induced by the AC being applied at these frequencies. I'm supposed to see this. It's supposed to look like that. I'm not supposed to see a dot only at all frequencies for 0 and for infinite. However, interestingly enough, when I put the load on, I do get a dot. Now, why is that? Well, for one reason, when our load impedance equals the characteristic impedance of the transmission line, my load's impedance is not transformed, so it's 50 ohms no matter what. But you'll notice on this zoomed in view, you can tell even though it's a little blurry, we're not exactly at 50 ohms. We're some point off, and in the demonstration I'll show you this where you can see it actually is not right on 50 ohms. There's going to be some error there. That's from the standard itself, not being precisely 50.0000, how many zeros you paid for. Any variation you're going to see in this value is just variation from the nominal value in the load. It's considered an error in the load. So before the video, I have preset some configurations in this instrument. That's why you see the layout that you do here with 2 traces and markers and some things here that I think are important to show as we go through things. But let's walk through the entire process of setting up the instrument outside of these things for measurement. First, we want to tell the instrument we want to do continuous measurement. So we can click on that. That, as you could tell by the green dot, was already set. We'll want to select our output power level. This is really dependent on what you're hooking up to it, and especially if you've got active devices, they may have an input level above which the instrument doesn't operate, not the instrument, but the device does not operate correctly. For the most of what we're going to do, it doesn't matter that much. We've selected our level as -10. Let me show you how we do that. This brings up the keyboard for this entry, labeled since I clicked on power level. And so I'm going to hit the minus sign, 10, and enter. And so now my output level is set to -10. I'm going to go to sweep. We're going to do a linear frequency sweep. I'm going to ignore these start and stop buttons. I want to use a different set of buttons to set the frequency later. But what's important is the number of points across our frequency sweep. The instrument can support up to 100,000 points. We're only going to do 10,000. Just like that. No real change for us, but wanted to show you how it was done. Then we're going to go set the frequency range. 10 megahertz to 2.9 gig. That sets our frequency range, and then our delta F, this step, is set by dividing this frequency range by 10,000. And so all the test points across the calibration are stepped in 289.029 kilohertz steps. It's all done for you automatically. Now that we've got that, let's do the calibration. So cal and other cals. Actually, before we do that, let's take a quick peek at port extensions and make sure that both ports 1 and 2, the port extensions are turned off. We don't want that to be on. Now we go to other cal, basic cal. We need to select what connectors we're using. We're using APC 3.5s. You can see here there's a long list of them. The drop down on this, we're selecting APC 3.5. By default, we come up to the Cal Poly Bench Cal Kit. That's what we want. It's named that way, so it will be first in the list. You can see if you click on it, there are other kits from which you can choose. Here's kit 828 that I pointed out earlier. Now we're going to do 1 port or 2 port. Here's where we enable the ports that we're going to be calibrating and using. I want to zoom in on this here to help make a point. Don't be misled. We're setting the type of connectors that are on the DUT, not on the end of our test cables making the reference plane. So in this case, our cables have male connectors, so the DUT has female connectors, as you can see that it's set right here. This makes a difference. The characteristics for the different types of connectors are different, so you have to get this right. Last, we have the calibration type. We're going to do an SOLT. Again, that's short, open, load, and through. You can see we have other types that we can do. And we click Next. So now we have a set of buttons for each port. So let's get started. Let's go to the shorts first. Attach the shorts. I'm sorry, I've been saying shorts. I actually got the opens. They're yellow. These are opens. It doesn't matter what order that we do them in. See, boom, it's just that quick. And now we've done both ports with the opens. Now we're going to disconnect these opens and go get the shorts. And the check marks tell us that it's completed the task. All right, time for the loads. And calibrate for each of our loads. Okay, time to do the through. So we remove the 50 ohm loads, and all the through is going to do is connect these two cables together. So a barrel connector is more than adequate. All right. You'll see this line here that kind of logically ties these two buttons together. We're only going to click one of them because it will do the task on both ports. There we go. We're done. And that completes our calibration. Put that away. Click Finish. Excuse me, and back to our screen we go. Looks a little funky right now. That's okay. Let's see about validating. So we are measuring S11, which means we're looking for the reflective measurement on port 1. So let's start with a short. And there we see the arc that we predicted to see. We start at 0 ohms. This is the low end of our sweep. And as we increase in frequency, we are seeing more reactance. That's what we would expect. Remember that the calibration data on these loads is not being applied. We are in measurement mode now. We are not in calibration mode, even though we have calibrated. We are calibrated. We are no longer in calibration mode. We are measuring. So that's why we see this. We can also take some confidence by looking at this green line here, which is our reflection coefficient. Here's 1 gig, here's 2 gig, here's 3 gig, and you can see our values for our reflection coefficient are extremely low. This is what we like to see. So we're happy with how our short looks. So now let's connect the open. Now technically, with nothing on there, I have an open, but it is not the open that we used. So let's attach the open on here. Here we see the arc. We expect to see this arc. Remember, we have stray capacitances, so we see the capacitive reactance across our sweep range. This is not unexpected. I don't necessarily care about the values so much as I know I'm expecting to see that. What gives me more confidence is, again, to look at my reflection coefficient here and see all the way out to 3 gig, we're pretty flat on spot on 1 for this open. So no surprises here at all. Now let's put the loads on. All right. So we've got our dots, and boy, at this point, it sure does look like we're spot on 50 ohms. And if we look here at the impedance measurement for the Smith chart side, for S11, we are like really, really close. Now you can, with this instrument, select a different scale. Now if I select my 0.1, I zoom in. Now you can see I'm not exactly on that 1J0 line. Let's zoom in a little bit more. Now you can see there's a lot of ambiguity going on there. There's a lot of measurements, but they're all clustered in right there at 50 ohms. That's what the marker is telling us, but I wanted you to see this so you could tell, oh yeah, there is some ambiguity to these measurements. All right, let's put the setting back where it belongs. There we go. All right, what do you say we do some measurements? Let's start with this thing right here. Now you notice that our impedance, they're clustered pretty close to 50 ohms. But notice that our reflection coefficient is way, way down there. Let's reselect this so we get our scale back. And we're down here just about to 0. But you also should notice that I hooked both cables up to it. We are actually doing a 2-port measurement. So if I go over here to recall, and I'm going to do a state recall and say, okay, show me instead S11 and S21 measurements. The S11 measurement is showing me my reflection coefficient. The S21 is showing me my losses through it. And if you look, my measurement, I'm 10 dB down. Well, that's because this is a 10 dB pad. So it's doing exactly what it's supposed to. And from a frequency perspective, we can see not only through it, but to it, that it's relatively flat. So this thing is working pretty well. We're pretty happy with that. All right, let's try something else. Sometimes these don't want to come apart as easily as I would like. Let's attach this and do another 2-port measurement. All right, so S11 is showing us that we are reflecting very little until this point right here, till we go screaming up, and then we start reflecting just about everything. This would be a gamma of 1. This is what this is reading for us as gamma. Down here on the S21 scale, we see that we are relatively flat at passing, and then we hit this knee here. What does this look like to you? Well, hopefully you're saying it looks like a low-pass filter, and indeed it is. So where do we find our knee? Well, we find our knee at the 3 dB down point. So using marker 1. So I'm going to go over here and I'm going to go to the marker screen and I'm going to select marker 1. Notice that I'm going to call my basic peak half a dB, minus 1/2 dB. So now my 3 dB point is going to be at minus 3.5 dB. So all I'm going to do is turn this knob here to change the frequency of my marker until it reads minus 3.5 dB, or as close as I'm going to get to it. That overshoots it by too much, so I'll go right there. And you could see that this is indeed a low-pass filter that rolls off at 1.4 gigahertz. See how easy that was? All right, let's do another one. One more device here. Hook this up. All right, oh, this looks a little different here. So we are reflecting a lot till we get to some point where we're not reflecting as much, and then real quickly we go back up again. If we look down here at S21, at looking through this unit, we definitely can look at this and say, this is a bandpass filter. All right, so what is our pass frequency, our center frequency? Well, let's spin the knob for marker 1 and put this back up at the top again. We can look at the reading and get our maximum. Looks to be about 1.7, minus 1.7. So we would determine the bandwidth by finding the 3 dB points, which would be minus 4.7 on either side. Now, we don't have enough point resolution here because we calibrated across 2.9 gig and we've got these 289, almost 300 kilohertz delta F. If we knew we were working with a filter that was centered at 920 meg, then we might do a 900 to 950 megahertz frequency range, divide that by 10,000 points, and then we'll get really nice granularity to find those accurate 3 dB points and give us a good idea of the bandwidth. Okay, so we've done some calibration validation, we've done some measurements. Let's do a quick review and wrap this thing up. All right, so calibration is an essential preparation when using the VNA. You got to get that right or your measurements just don't work. It takes care of the influence that the test setup has, allows for what your cables and your connectors are doing, accounts for the delays, the stray reactances, and all of that kind of information so that you get an accurate measurement of your device under test. The calibration standards that are part of your calibration kit, they're already known to the VNA. That's why it's important that you select the correct cal kit and make sure that you use the right gender connectors and all of that because they all have unique values. The VNA makes life much easier by automating all of this process, and hopefully you can see that by understanding how the VNA works and interacts with calibration and then validating that calibration, that you can assure that you have accurate measurements. And with that, that's all I got for now. Thanks for watching the video.